In this video, we're going to look at balancing chemical reaction equations. Now, the first question you might be asking is, why do we even care? Why do we even need to do this? Well, the reason why is because we want our chemical reaction equations. We want this right here. This is a chemical reaction equation. We want that to represent the law of conservation of mass. Now, the law of conservation of mass tells us that before and after any sort of change happens, mass has to stay the same. So our total number of particles of each type of atom needs to stay the same, even if they're bonded in different ways. So we need our chemical reaction equation to show this. So our Y is the law of conservation of mass. And this is going to become even more important later when we start to do math and calculations with this, because those coefficients that we're going to add when we balance these chemical reaction equations are going to become super important. So before we jump into actually balancing, let's look at kind of the anatomy of a chemical reaction equation. So you're always going to have something on the left, something on the right, and an arrow in between. So what you're starting with, what's on the left side of your arrow, is those are your reactants. Those are your starting materials. What's on the right side of your arrow, those are your products. Those are what you're making at the end. Now, a lot of this we already know. We know chemical formulas. We know what the subscripts mean. There might even be in some of them a state of matter, so a parentheses with a letter. So our states of matter are solid, liquid, and gas. So if you see a parentheses with either an S, an L, or a G, that's telling you the state of matter. What's new when we balance, and this is what the only thing we're going to be changing when we balance a chemical reaction equation, are these big numbers right here. Those are the coefficients. And our coefficients tell us two different things. Our coefficients tell us the number of moles of each type of particle, and our coefficients tell us the number of particles. So since we're going to be drawing particle diagrams and thinking of this right now on a particle level scale, these coefficients are going to tell us how many particles of each type. So when we go to balance a chemical reaction equation, the only thing that we are ever allowed to change are the coefficients. You can't change the subscripts, you can't change the chemical formulas, you can't add any more additional formulas. The only thing you can change are your coefficients. So those are the constraints that we're going to work in. And we're going to start just by looking at an already balanced chemical reaction equation, and we're going to draw a particle diagram for it, just so that we can help visualize this a little bit more. So before I can draw my particle diagram, I need to assign some symbols. So I'm going to make my phosphoruses triangles, and I'm going to make my oxygens circles. So this reaction equation tells me that my reactants, I have one P4, so P4 is going to be 4 triangles stuck together. And then I have 3 O2s. So an O2 looks like 2 circles stuck together, and I have 3 of them because that's what my coefficient tells me. In my product side, I have only one compound. I have P2O3, and I have 2 of them. So one P2O3 would be 2 triangles and 3 circles, and I have 2 of them, so I need another one. So 2 triangles and 3 circles. Now, if I wanted to check the law of conservation of mass, I'm going to check to make sure that I have the same number of triangles and the same number of circles before and after. So I have 1, 2, 3, 4 triangles. I have 1, 2, 3, 4 triangles. So that's good. And then I'm going to check my oxygens. I have 6 over here. 1, 2, 3, 4, 5, 6. So I should have 6 after. 1, 2, 3, 4, 5, 6. So that helps us visualize by drawing this particle diagram. It helps us see how our total number is staying the same even though they're being bonded a little bit differently. So let's look at a different type of example. So in this one, the particle diagram is already drawn for you. And then the reaction down here has blanks. It does not have any coefficients. So we're going to balance this based off of our particle diagram. So our H's are squares, nitrogens are triangles, O's are circles. So this looks like we only have one type of compound, which matches down here. We have an HNO3, so there's our HNO3. since we have 2 of them, I'm going to put a 2 in front. And then over here, I have 2 products. I have an N2O5 and I have an H2O, and I only have 1 of each. So I'm going to go ahead and put 1s there. And just to double check and make sure that I didn't make any mistakes when I drew the particle diagram to start with, I'm going to check to make sure that I have the same number of squares and triangles and circles before and after. So I have 2 squares, I have 2 squares, I have 2 triangles, I have 2 triangles, and I have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 circles. So I'm good. Now I want to make a note here. On the previous example, the P4 didn't have a number in front of it. So similarly, when we write chemical formulas, like here, if we just have the element symbol but no subscript, it's assumed that it's a 1, and we don't have to write the 1s there. Same goes with the coefficients. We don't have to write a 1. So if you were to see this reaction equation already balanced, what you'd see is 2HNO3 goes to N2O5 plus H2O. It's helpful for our purposes, though, if we're filling in the blanks, to put the 1s, just to make sure that we know that we didn't accidentally forget to put something there. But you don't have to put the 1s as coefficients when you're writing balanced chemical reaction equations.